Hello and welcome to this R tutorial. So in the previous section, we introduced the multi-armed bandit problem for this ad click-through rate optimization problem, and we already tried two algorithms. The first algorithm was the simple random selection algorithm that consists of selecting at pure random an ad at each round, and this algorithm gave us a total reward of 1,200 on average, because there is this random factor, but on average we got 1,200 total reward. And of course, when we plotted the histogram, every ad was selected more or less the same number of times. And then we tried another algorithm, which was the upper confidence bound algorithm, and there we got much better results. Because not only we managed to almost double the total reward, because we got a total reward of 2,178, so almost the double of what we obtained with the random selection. And the even better thing is that we managed to figure out which ad version was the best to show to the user. That is, which ad version had the highest conversion rate, the highest CTR, that is the highest click-through rate. And now, in this section, we are going to try a new algorithm, which is called Thompson sampling. And so, in this section, we're going to look at two things. First thing is, can Thompson sampling beat the upper confidence bound? That is, can Thompson sampling give us a total reward that is even higher than 2,178? We almost doubled the total reward of random selection. Let's see if we can beat that again, like more than double it or even triple it. I don't know. Let's see. And the second thing that we're going to look at is if we get the same ad version that has the highest conversion rate. Let's see if we get ad version number 5, which was the ad found by the upper confidence bound algorithm. It found ad version number 5. So let's hope that we also get the ad version number 5. This should logically be the case if we manage to beat upper confidence bound in terms of total reward. So let's do this. Let's implement Thompson sampling in this section. We're actually going to do that in one step, because when you think about it, we will only need to change the strategy here in this for n loop and then keep the same to implement Thompson sampling, because we'll keep these parameters here, that is this number of rounds, this number of ads, this ad selected vector that contains all the different ads selected at each round, and this we will need to change because these are the parameters of the upper confidence bound algorithm, so we will need to change it. And of course, we will keep this total reward because we want to get the total reward accumulated through the execution of this Thompson sampling algorithm. So what we're going to do now is simply take everything from here to here, copy, and then paste it here. And we will only change what we need to change, that is, the right parameters for the Thompson sampling algorithm. All right, so let's do it. We can already replace UCB here by Thompson sampling. And now let's change the strategy. But before, let's start with the basics. Let's set the right folder as working directory. So let's go to our machine learning AZ folder, then part 6, reinforcement learning, Thompson sampling, and then make sure that you have this as CTR optimization CSV file. That is, of course, the same CSV file as the one we had in upper confidence bound. So if you have this data set, you're now ready to click on this More button here and then set as working directory. All right, so now let's implement our Thompson sampling algorithm. So let's directly jump to the slide of the Thompson sampling algorithm. All right, so what do we see here? This Thompson sampling algorithm takes 3 steps. First step is, at each round, we need to consider 2 numbers for each ad I. The first number is the number of times the ad I got reward 1 up to round n, and the second number is the number of times the ad I got reward 0 up to round n. So that's the first thing we'll do here. We will consider these parameters and declare the variables corresponding to these parameters. And we can notice that if we compare this Thompson sampling algorithm to the UCB algorithm, well, it's the same step 1 with different parameters, because as you can notice here, in the step 1 of the upper confidence bound algorithm, we also consider 2 numbers. And these 2 numbers are the number of times the ad I was selected up to round n, and the sum of rewards of the ad I up to round n. So if we have a look at this code section here, which is the code section for the upper confidence bound algorithm, well, we can see that these 2 parameters are here and that these parameters are no longer the parameters for Thompson sampling. And these two parameters that we considered in step 1 in the UCB algorithm are actually replaced by two new parameters in the Thompson sampling algorithm. So what we'll do right now is simply to remove these two parameters that are the parameters considered in the step 1 of the UCB algorithm and replace them by these two new parameters that we need to consider for Thompson sampling algorithm. So let's replace them right away, and therefore let's declare two new variables. So first number, the number of times the add I got reward 1 up to round n. So let's call this number numbers of rewards, and then underscore and 1 to specify that it's the number of times the add got reward 1. And then the second number is the number of times the add I got reward 0 up to round n. So same, we're going to create this variable numbers of rewards 0. Now, what are going to be these two variables? So these are the parameters of Thompson sampling at the essence of the future strategy that we're going to have here. So these two variables here are going to be some vectors of d elements, that is 10 elements, and as you might have guessed, they will contain for each add the number of times they got rewards 1 up to round n and 0 up to round n. So we're going to initialize these vectors the same way as we did for upper confidence bound. That is, we're going to take this integer d that creates a vector of d elements, and those d elements are zeros. So that's exactly how we're going to initialize these two variables here by a vector of 10 zeros. Because of course, at the beginning, the number of rewards of each add is of course 0, because simply each add wasn't selected yet. Alright, so we have our two arguments. That means that step 1 is done, and we can move on to step 2. So step 2 is, for each add I, we take a random draw from this distribution below, which is the beta distribution. And why is that? It's because we have two important assumptions here, which are related to Bayesian inference. So the first assumption is this first line here. We suppose that each add I gets rewards from a Bernoulli distribution of parameter theta I, which is the probability of success. And you can picture this probability of success by showing the add to a huge amount of users, like 1 million users, and theta I could be interpreted as the number of times the add got reward 1, that is the number of successes, divided by this total number of times we selected the add, that is 1 million. So basically theta I is the probability of success, that is the probability of getting reward 1 when we select the add. And so the assumption is that each add I gets rewards 0 and 1 from this Bernoulli distribution of parameter theta I, which is the probability of success. And then the second assumption, a less strong assumption than the first one, which is the strongest assumption, but we have this second assumption, which is this second line here, and that is that we assume that theta I has a uniform distribution, which is the prior distribution. And then we use the Bayes rule to get the posterior distribution, which is p theta I given the rewards that we got up to the round n. And so by using Bayes rule, that's how we get this beta distribution in this step 2 here. And so by taking at each round these random draws of these beta distribution, well, since these random draws represent nothing else than this probability of success, we get the strategy here, which is to take the maximum of these random draws, because the maximum of these random draws is approximating the highest probability of success. And that's the whole idea behind Thompson sampling. It's that we are trying to estimate these parameter thetas that are the probability of success of each of these 10 adds. Then by taking these random draws and taking the highest of them, we are estimating the highest probability of success. And this highest probability of success corresponds to one specific add at each round. So when we take these random draws at a specific round, we might be wrong. But when we take these random draws over thousands of rounds, well, just based on the essence of probability, we obtain overall the theta that corresponds to the add that has the highest probability of success. That is the highest probability of getting reward equals 1. And that's the idea behind Thompson sampling. And by the way, taking these maximum of these random draws, that is this maximum of these estimations of the probability of getting reward equals 1, well, that's nothing else but step 3. And so right now what we'll do is to implement this strategy composed of step 2 and step 3 in this code section here, replacing the old strategy of getting the upper confidence bound. Okay, so let's do it efficiently. Let's keep the logic behind this code section. Let's not delete everything too quickly. You know, since we'll get the different random draws of each add at each round, And since we need to take this highest random draw, well, we should keep this coding strategy here that gets the maximum value of something. So we'll replace this max upper bound here by a max random, because in the UCB algorithm we needed to take the maximum upper confidence bound, and here for Thompson sampling we need to take the maximum random draw. So we call this maximum random draw max random. All right, and then of course we keep this add equals 0 because that's just to initialize the add that will select at a specific round, because of course with Thompson sampling we will need to pick an add to show to the user. So we will keep this add equals 0 and this add equals I here, but then what we absolutely need to change here is this if else, because this if else is directly specific to the upper confidence bound strategy. So we will remove this, and now we will implement the Thompson sampling strategy. So first thing we need to do is to generate the random draws of each of the 10 adds. So we keep this for I in 1D because we will need this loop to go through the 10 adds, and so now we need to take the random draws. So we're going to declare here a new variable that we'll call random underscore beta, and that of course will correspond to the different random draws because these are random draws taken from the beta distribution. So then equals, and now we're going to use a function of R, which is the R beta function, which will give us exactly what we want. That is, it will give us some random draws of the beta distribution of parameters that we choose. And as we can see on this slide here, the first parameter is the number of times the add version I got reward 1 plus 1, and the second parameter is the number of times the add I got reward 0 plus 1. So let's do it. Let's press F1 here to get some info about this R beta function. So we will need only 3 of these arguments here. The first argument we need is n, the number of observations. So here n equals 1 because we only want to take one random draw. And then shape 1 and shape 2 are the 2 parameters of our beta distribution. That is, shape 1 is the number of times the add got reward 1 plus 1, and shape 2 is the number of times the add got reward 0 plus 1. So here for shape 1 we input shape 1 equals numbers of rewards 1. And of course, since this corresponds to a specific add, I will add some brackets here and take the add version I that we're dealing with at the specific time in this for I loop here. That is, this corresponds to a specific add. And let's not forget the plus 1 here, and then comma to input the second parameter. And of course, the second parameter is going to be the ith index of this numbers of reward 0 vector. And then let's not forget the plus 1 here. And that's our 2 parameters of this beta distribution from which we're getting the random draws. Okay, so we have everything we need. And now, of course, we will need to play with this if condition here to get the maximum of these random draws. So a good exercise for you would be to pause on this video and try to finish this code section here to guess the last elements of this code here. So I'm going to tell you right now. Well, right now we need to take the maximum of these random draws. We already declared this max random variable here that will be this maximum of these random draws. And so, well, you guessed that now we need to replace this max upper bound here by max random. And here, of course, we need to replace this upper bound here by random beta. Okay? And then same here, we replace max upper bound here by max random and upper bound here by random beta. And eventually, of course, we keep this add equals I here. Okay, so let's re-explain quickly what's happening here. For each add I in this for I loop here, well, we're taking a random draw from this beta distribution of parameters, number of times the add got reward 1 plus 1, and number of times the add got reward 0 plus 1. And then each time we take a random draw from this distribution, well, we check to see if this random draw is higher than this max random here. So of course, for the first add, this will be the case because max random was initialized to 0. So this condition will be true for the first add, and therefore max random will be equal to this first random draw here. And so we keep this first add here. And then when we move on to the next add, what happens is that we take another random draw from this beta distribution of these parameters here that corresponds to this new add I. And then, if this new random draw is higher than this max random here that was equal to the previous random draw, well, that means that this condition is true, and therefore max random takes the value of this new random draw, and therefore we select this new add version I here that has the highest random draw, and we forget about the previous add that was selected because simply it has a lower random draw. Alright, so that's the idea, and that's the strategy of Thompson sampling that we are implementing at each round. Great, so now we almost have everything we need. The thing that we need to update now is what's happening here, because this comes from the upper confidence bound algorithm. So this is, the parameter of step 1 in the UCB algorithm. So we will need to remove this line. We don't need this. And we have to keep this because this is to get the real reward, as we explained in the UCB algorithm. This is actually how we proceed to get the reward in this simulation data set. And then what do we have? We have this line containing the sums of rewards. And of course, the sums of rewards is a parameter of the UCB algorithm. So we need to remove that as well. And now we are ready to update what we need to update for the Thompson sampling algorithm. All right, and then we have the total reward that of course we must keep because this is the exciting result. And this is kind of a performance evaluator. So now, according to you, what do we need to update? Well, of course, what we need to update are these two vectors here, numbers of rewards 1 and numbers of rewards 0. Because, in this strategy here, we are inputting the ith index of these two vectors. But we need to update them at each round because otherwise they will always be equal to 0 because they were initialized as 0. So now what do we need to do? We need to increment their values when we get the reward. So let's see what we need to increment. For this variable here, the numbers of rewards 1, well, these corresponds to the different numbers of times each add got reward 1 at round n. So we need to increment it only when the add got reward 1. And what about this vector? Well, that's the same. That's the vector containing the different numbers of times each add got reward 0 up to round n. And so we need to increment this vector only when the add that we selected got reward 0. So since this depends on the reward we get when we select the add, we will need an if condition. And so we're going to write this if condition here, if. And so the condition is simply if reward equals 1. So if this reward we get at this specific round when we select this specific add here, if this reward is 1, then what do we need to do? We need to increment this numbers of rewards 1, but only for the index add, because this index add here corresponds to the index of the add that was selected. So let's do it. Let's increment this numbers of rewards 1. Let's copy that and let's paste it here. And now let's take the add index corresponding to the index of the add that was selected. And then that's where we need to increment it. So I'm going to copy this and paste it here and add a +1. All right, so when reward is 1, well, of course, what we need to do is to add a +1 to the number of times this add here got reward 1. All right, and then we have this else. And this else corresponds to the situation where reward here is equal to 0. That is when the add that we selected got a 0 reward at this specific round n. And therefore, when that happens, we need to increment the numbers of rewards 0 this time. So I'm copying this line and pasting it right here, and then replace the index I by add, because we need to increment the numbers of rewards 0, but only for the value corresponding to this add index here. All right, and now we're done. Thompson sampling is actually fully implemented. So now, time for the exciting step, visualizing the results. So we'll do that in the next tutorial, and until then, enjoy machine learning!